Hi everyone, I am Harvey Labis Abiagador, and in this video, I will show my solution for the take-home quiz under the topic Z-transform. Before we go to my solution, let me introduce first the Z-transform pair table. So here is the table, and if you notice, I added one Z-transform pair, and this transform pair will be relevant in a certain problem. For the first problem, find the inverse Z-transform of x of z equals to 10z over z squared minus z plus 1. So if we consult at the table, then we can say that number 9 is the most logical or most sensible transform pair to use. So if we use 9, we must find a way that the denominator must match this denominator and the numerator must match at this numerator. So if we look at this part, you have negative z, and for this one we have 2c cos a. So therefore, we must find a way that 2 cos of a is equals to 1. So if we let that, so that becomes cos of a equals 1 half. Then if we try to find the a, that is cos inverse of 1 half. And if we put that in the calculator in radian mode, you will get a equals to pi over 3. So when a is equals to pi over 3, then we plug it in here for the numerator part. That is z sine a is equals to z sine pi over 3 is equals to square root of 3 over 2 times z. So now we must find a way that this one will appear in the numerator. Okay, so for the given, we have in the numerator part we have 10z. Then if we force to put square root of 3 over 2 times z here, so we must find a way to counteract those things that we forced to put. Okay, so as a counteract, let's divide 10 over square root of 3 over 2, so that when you multiply these two, that will just result to 10z. Okay, so now we can rewrite xc is equals to 10 over square root of 3 over 2 times square root of 3 over 2z over z squared minus z plus 1. So this part is the 10z. Okay, so now if we transform it in a form that is recognizable to this one, that is 10 over square root of 3 divided by 2 times z sine pi over 3. So if you notice, this one is just equals to this one, so z sine pi over 3 over z squared minus 2 cos pi over 3 plus 1. So this one is just equals to negative c. Okay, so nothing has changed in terms of the value, but the form has changed so that it will fit in this part. So using 9 from the table, we can find the inverse z transform, which is x of n is equals to, so 10 over square root of 3 over 2. So we took out the constant since z transform obeys linearity. For this one, if you look at the table, we can say that the whole or the inverse z transform of the given x of z is equals to 11.5470 sine pi over 3 times n u of n. For number 2, find the inverse z transform of x of z equals to z raised to the power of negative 4 over z minus 1 plus z raised to the power of negative 6 plus z raised to the power of negative 3 over z plus 0.5. So for this part, first term, z raised to the power of negative 4 over z minus 1. So this part exponent suggests shifting. So this part is the shifting. We pick the number 3 as the x of z because of the denominator. Okay, so therefore we have z raised to the power of negative 4 over z minus 1 equals to z raised to the power of negative m times a of z over z minus 1. So using this part, we let z raised to the power of negative m a z is equals to z raised to the power of negative 4. So that's for the numerator. Okay, so this part is a z raised to the power of negative m plus 1 is equals to z raised to the power of negative 4. Therefore, negative m plus 1 equals negative 4, which implies m equals 5. Then also a equals 1. So there's 1. If we transform that into a form that can be used for number 3, we have z raised to the power of negative m, which is 5, then z over z minus 1. So if we take the inverse of this one, inverse z transform, we get u of n minus 5 for this part. Okay, for the second part, a z raised to the power of negative 6. So we can rewrite z raised to the power of negative 6 as this one. We multiplied 1. And we know that 1 has inverse if we look at the table 2. Okay, so the inverse of this one is just the Dirac delta, but we have this part, so which it means that that is shifted. So we have Dirac of n minus 6. Okay, so for the last term, z raised to the power of negative 3 over z plus 0.5, these parts are just shifting, and x of z that we pick is the 6th in the table because of its denominator. So this is the a. Okay, so we're using this one, we let z raised to the power of negative m times c equals to z raised to the power of negative 3, so that's from the numerator. So that is z raised to the power of negative m plus 1 equals z raised to the power of negative 3. Therefore, negative m plus 1 equals negative 3, which implies m equals 4. So for the denominator, z plus 0.5 equals z minus a. So therefore, 0.5 equals negative a, which implies a equals negative 0.5. So now we can rewrite this given into this form. This is usable with the table. So we get z raised to the power of negative 4 times z over z minus negative 0.5. So if we take the inverse of this one, so we get negative 0.5 raised to the power of n minus 4 u n minus 4. So this, we have n minus 4 here because of the shifting. So by linearity property, we just add those individual z transform, and we get as the final answer x of n equals u of n minus 5 plus the Dirac n minus 6 plus negative 0.5 raised to the power of raised to the power of n minus 4 u n minus 4. For number 3, find the inverse z transform of x of z equals to 1 over quantity 1 minus z raised to the power of negative 1 times quantity 1 minus 0.5 z raised to the power of negative 1. So if we look at the z transform table, we notice that there is no z raised to the power of negative 1 in the denominator. So we multiply the right hand side by z squared over z squared, or just 1. So if we multiply it, that z squared over z squared, so we get z squared over this z times this part, and then z times this part. So if we distribute the z, you get z squared over z minus 1 times z minus 0.5. Because of this, because we did this, we have now this part which is present in the table. Okay, so but most z transform has z in the numerator. We need to spare z to be pulled back after doing partial fraction. So you will see later when I say this. Therefore, we divide both sides by z. Okay, so x of z over z is equals to z, that was z squared before, over z minus 1 times z minus 0.5. So this part is saying that if we have z here, then if we arrive after the result of the partial fraction, then we can just multiply z so that there's z in the numerator. Okay, so by partial fraction, so we take the partial fraction of this one, we get this part then is equals to a over z minus 1 plus b over z minus 0.5. So I hope you're familiar with the partial fraction technique. So solving for a, we multiply both sides by z minus 1. So this becomes z over, so z minus 1 just cancel. So we left with z minus 0.5 equals to a, because z minus 1 just cancel, or equals to what becomes 1. Then plus c minus 1 times b over z minus 0.5. So to get rid of this b, we let z equals 1. Okay, so this becomes 0. So as a result, we get 1 over 1 minus 0.5 is equals to a, which implies a equals 2. Solving for b, we multiply both sides by z minus 0.5. So this part, we multiply this by z minus 0.5. So we get z over z minus 1 equals z minus 0.5 times a over z minus 1 plus b. Now we let z equals 0.5 to cancel a, so this becomes 0 if we did that. So we get 0.5 over 0.5 minus 1 equals b, which means b equals to negative 1. Therefore, x of z over z, this one can be written as 2 over z minus 1 plus negative 1 over z minus 0.5. Now, if we multiply both sides by z, we get x of z equals 2z over z minus 1 minus z over z minus 0.5. So using that result, we get this one. Okay, we can now take the individual inverse of this one, this and this. The inverse of 2z over z minus 1. So if we look at the number t in the table, we get 2 times u of n for this part. And then using number 6 for this part, that is z over z minus 0.5. So we get 0.5 raised to the power of n times u of n. Okay, since z transform obeys linearity, we can just add those two individual inverse to get the whole inverse of our x of z. And that is x of n is equals to 2 times u of n minus 0.5 raised to the power of n u of n. For number 4, find y of n if y of z equals z squared times z plus 1 over z minus 1 times z squared minus z plus 0.5. Most of z transform has z in the numerator. Therefore, we need to spare z to be pulled back after doing partial fraction by dividing both sides by z. So just like what we did in number 3. If we divide both sides by z, y of z over z equals z plus 1 all over z minus 1 times z squared minus z plus 0.5. So later, when we're done with the partial fraction, we can just take back or multiply both sides by z so that we have z in the numerator. That's what the meaning of this part. Now, for this part, we can just obtain the roots so that we can factor it. Obtaining the roots using quadratic equation, so we get c equals to this 1, negative times negative 1 plus or minus squared of negative 1 squared minus 4 times 0.5 over 2 times 1. So solving that, we get c equals 0.5 plus or minus j, because this one is square root of negative 1 and that is j, so j 0.5. Okay, the presence of imaginary numbers suggests 15, because if you look at the table, the 15 involves the imaginary number. Based on those formula, okay, if we let p equals 0.5 plus j 0.5 and its conjugate p conjugate equals 0.5 minus j 0.5. So therefore, we can write y of z over z, so this one as z times z plus 1 all over z minus 1, and in this part becomes z minus p multiplied to quantity z minus p conjugate. Okay, by partial fraction, this part can be represented as b over z minus 1 plus a over z minus p plus a conjugate over z minus p conjugate. This part is based on our number 15, so I highly suggest you look at our number 15 so that you can understand this part. Okay, start with b first. Solving for b, which means we multiply both sides by z minus 1. So if we did that, we get z times z plus 1 over z minus p times z minus p conjugate equals to b plus z minus 1a over z minus p plus z minus 1a conjugate over z minus p conjugate. To cancel a and a conjugate, we let c equals 1. Therefore, 1 times 1 plus 1 all over 1 minus p times 1 minus p conjugate equals b. This suggests using this p and p conjugate based on here, we get b equals 4. Okay, so now we have b. Let's move on to a. Solving for a, we multiply both sides by z minus p. If we did that, z times z plus 1 all over z minus 1 times z minus p conjugate. That is equals to z minus p times b over z minus 1 plus just the a plus z minus p a conjugate over z minus p conjugate. Let z equals p to cancel b and a. If you do that, you get p times p plus 1 over p minus 1 times p minus p conjugate. That will result to a. If you use this definition of p and p conjugate, we arrive at this a equals to negative 1.5 minus j 0.5. And if you take the polar form, you get the 1.258114 with angle negative 2.8198 radian. Just a tip to solve this one in a calculator, it is easier to solve this one if you store the value of p and a p conjugate in a variable and just substitute it whenever you need it in the expression. We have b and a, so now let's move on to a conjugate. Notice that we have a here, so we can just take the conjugate of that, but just to make sure, we will solve also the a conjugate. We multiply both sides by z minus p conjugate, so that becomes z times z plus 1 all over z minus 1 times z minus p. That is equals to z minus p conjugate times b over z minus 1 plus z minus p conjugate a over z minus p plus a conjugate. So if we let z equals p conjugate to cancel b and a, we get p conjugate times p conjugate plus 1, p conjugate minus 1 times p conjugate minus p. That will equal to a conjugate. Using the definition of this one, the p conjugate and the p, we arrive at this a conjugate equals to negative 3 over 2 plus j 1 half. And if you take the polar form of this one, we get a conjugate equals 1 minus 58114 with angle 2.8198 rad. This confirms that this is the a conjugate of this a. Now we can write y of z over z as we have our b, so that is 4 over z minus 1 plus a, this a over z minus p plus this one is conjugate over z minus conjugate. So if we multiply both sides by z, we get y of z equals 4z over z minus 1 plus az over z minus p plus a conjugate z over z minus p conjugate. Notice that I just put the variable because it's very long to put the whole or the value of these variables, but it will serve its purpose. For this one, just look at the table 3, and for this one, just look at the table 15, which I include for this slide. So recall that p equals this part and its polar form is just 0.7071 with angle 0.785 for radian, and a equals this one with polar form 1.58114 with angle negative 2.8198 radian. So using number 3, number 15 formula and the linearity property, we have this y of n, a very lengthy one, and the final expression for y of n is equals to 4 u of n plus 3.1623 times 0.7071 raised to power of n cos 0.785 for n minus 2.8198 radian multiplied to u of n. This one is just based to this one, so if you just substitute those values based on this one, we get this expression for the inverse of y of z. And lastly, for number 5, find x of n if x of z is equals to z squared over z minus 1 times z minus 0.5 squared. So again, most of z transform has z in the numerator. Therefore, we need to spare z to be pulled back after doing partial fraction, just like what we did in the previous items. As a strategy, we divide both sides by z. So this will result to x of z over z equals to z over z minus 1 z minus 0.5 squared. So using this expression, we take the partial fraction of this one. We have z over z minus 1 times z minus 0.5 squared equals to a over z minus 1 plus p over z minus 0.5 plus c over z minus 0.5 squared. Solving for a, multiply both sides by z minus 1. Okay, so we multiply this both sides of this by z minus 1, we get z over z minus 0.5 squared equals a plus z minus 1 times b over z minus 0.5 plus z minus 1 times c over z minus 0.5 squared. Now we let z equals 1 to cancel b and c. So when that happens, we have 1 over 1 minus 0.5 squared equals a, which implies a equals 4. Solving for c, multiply both sides by z minus 0.5 squared. So if we do that, we have z over z minus 1 is equals to z minus 0.5 squared times a over z minus 1 plus z minus 0.5 squared times b over z minus 0.5 plus c. So to cancel a and b, we'll let z equals 0.5. So therefore, we have 0.5 over 0.5 minus 1 is equals to c, which means z equals to negative 1. Solve for b. Given that a equals 4 and c equals negative 1, so we'll let z equals 0 for easier calculation, because if you look at the equation, we have a and c. For whatever value of z, we can just substitute it and take the value or get the value of b. That's what we're doing in this part. If we let z equals 0, so this part becomes 0 equals 4 over negative 1 plus b over negative 0.5 minus 1 over negative 0.5 squared. So simplify, 0 equals, this part is negative 4, this part is negative 2b, and this part is just equals to negative 4. So therefore, 2b equals negative 8, which suggests b equals to negative 4. Now we can rewrite this equation as x of z over z is equals to 4 over z minus 1 minus 4 over z minus 0.5 minus 1 over z minus 0.5 squared. Now, we multiply both sides by z, so we can have z in the numerator of these terms. We have this x of z equals 4z over z minus 1 minus 4z over z minus 0.5 minus z over z minus 0.5 squared. Solving for the individual inverse transform for this one first, if you look at number 3 in the table, you get the inverse of this one is just 4 u of n. For this one also, 4z over z minus 0.5, if you look at number 6 on the table and used it, you get 4 times 0.5 raised to the power of n u of n. And for the last term, that is z over z minus 0.5 squared, then you use the number 8 in the table. If you take the inverse transform of this one, so first we need to manipulate it so that we can use number 8. So we can use number 8 if we have a here and a here as well. So we forced to put a here, which is 0.5, and in order to counteract that, we must divide this one by 0.5. So 1 over 0.5, that is just equals to 2, and then just take the inverse z transform of this one, so we have n 0.5 raised to the power of n u of n. By linearity property, we can just add those individual z transform. We get x of n as our final answer equals to 4 u of n minus 4 times 0.5 raised to the power of n u of n minus 2n 0.5 raised to the power of n times u of n. That would be all. Thank you.